Hello, I'm Gilles Callebaut. I will present a joint work by KU Leuven and Lund University done in the context of the Horizon 2020 project Reindeer. In the Reindeer project, we investigate a new paradigm called RadioWeaves. In RadioWeaves, we move from the conventional case where antennas are closely located together to the scenario where the users or the devices are surrounded by antennas. As a consequence, we have an abundance of resources, but also a wide variety of applications to serve. At the left-hand side, you can see some of the expected applications of the RadioWeave network, and next to it, our RadioWeave infrastructure tactile, where we have 280 RF chains covering the full indoor environment, the room. And in Reindeer, we look at applications such as UVs, energy neutral augmented reality, tracking of goods. So these applications have different requirements and restrictions. So we come back to the main question of this work, which is for how do we share these resources in RadioWeave for these different application requirements. Furthermore, as we foresee in RadioWeaves, these networks will not only provide communication, but also sensing, positioning, and wireless power transfer. So consequently, some new terminology is in order. So the conventional access points are thereby required to be extended with additional hardware and functionality to provide also localization and power transfer. So we need to redefine these access points as we commonly or conventionally use as contact service points denoted by CSP or abbreviated as CSP to highlight that there is a first contact point from the perspective of the devices and also not to confuse these CSPs with the conventional access points which only provide communication. These CSPs can have different resources, can have one antenna, more antennas, or even none. More information about this terminology can be found in the reference paper at the bottom of the slides. So the main message here is that we have a new term called CSP, which we'll be using in this video, which resembles the conventional access points, but are extended with more functionality. So the general challenges in constructing such a radio wave network are the necessary support of very distinct applications, while also ensuring that all the available resources are distributed fairly among these applications. As we have a very high number of resources available, it is our task as engineers to also carefully use these CSPs and try to minimize the energy expenditure of the full RadioWeaves infrastructure by, for instance, putting unused resources, CSPs, to sleep. In order to have a coherent operation, these CSPs need to cooperate and synchronize. There is also the question of scalability versus cost. And at the end, it all boils down to we need to support an heterogeneous system where some of the CSPs are connected, for instance, in a tree topology, while others are connected in a daisy chain topology. So, and we also have different resources available inside of the CSPs. This all emphasizes that we need clever optimizations of the available resources in RadioWeaves. So the idea is to orchestrate different federations, so which have some CSPs allocated to them and to serve a number of devices inside of this federation. We illustrate this by dividing our network in 4 logical groups, these federations, which here serves a very specific application. So each federation serves a distinct application. We have, for instance, a federation providing system broadcast information, augmented reality, UV applications, and so on. So why do we need this federation? Why not try to serve all users, all applications with a full infrastructure? Well, this is due to the different requirements, as I said before, of these applications. For instance, the UV application requires that we can estimate the position accurately, meaning that we need spatial diversity created by choosing CSPs which are spread all around the infrastructure. And because it has a certain mobility, these federations also need to follow these UVs when moving. Next to that, we have these energy neutral augmented reality goggles, which require high data rate, low latency, and wireless power transfer. So in contrast to the UV application, CSPs located closely together are probably a better fit because it reduces the latency, because it doesn't need to communicate with all the CSPs in the full RadioWeaves infrastructure, and also because it's closely located to the user or the goggles. This is better for the wireless power transfer. So what are our tools? Well, first, to orchestrate these federations, we have constructed a Python framework. The framework is online and open source, available in the GitHub, and it's done in the context, or the implementation is done in the context of a master thesis subject, which is also referenced below. So we can divide these federation orchestrations in 5 different subproblems. So the first one is the collection of input information from the RadioWeaves infrastructure, the UVs, and other sources, channel models, and so on. So based on that, by modeling and prediction, or we can model and predict the application level performance metrics for a certain application. And then we need to evaluate our resource allocation solutions that we have done, and we need to perform the resource allocation in turn. And then we need to do this in a dynamic way to update according to the movement of UVs, new user equipments entering the infrastructure. So in order to determine a good assignment of the UEs and the CSPs to these federations, we need to define the utility that UEs and their applications derive by being served by a particular constellation of CSPs. So each UE or set of UEs needs defined by utility function specifying the value given by the set of serving CSPs. So this is done by the Oracle, where we put in a set of user equipments, a set of CSPs available, and all these input data, the available data, and based on that, the Oracle outputs the utility function for a set of users served by a certain federation. What we can do is we can exhaustively search or query this Oracle to get the utility function for a set of UEs and a set of CSPs and optimize it that way, which is of course not possible to do this in this way. So we need to have a more clever way, and we need to define the problem of federation orchestration and use an heuristic and more approximation methods to derive this utility and to orchestrate these federations. So first question is how to group these users to form a set of users, how to allocate a set of CSPs to that group of users or the federation, and how to define the overall utility of the federation. So first, we'll check the user equipment utility. So we define it here as the U stands for utility. We have a user which has some CSPs assigned to it, to a specific federation for that user. And what we here see is that we want, for a set of performance metrics, we take the difference between the value of the performance for that particular user served by that particular set of CSPs, which is subtracted by the minimum required value of that performance metric. So the minimum of this overall performance metric defines the overall utility of the user equipment. So in the end, we can have a binary application where the utility becomes 1 if all these values of these performance metrics exceed the minimum required performance value. For example, for wireless power transfer, it could be sufficient that we provide a certain a milliwatt, let's say 1 milliwatt, for instance, and that's enough. Providing 2 doesn't add more to the application. 1 is enough, so the utility becomes 1 when you can support 1 milliwatt of power transfer and becomes 0 when you cannot. Other applications can use waiting, for instance, to wait to sum over all these performance metrics and apply a weighting to them to prioritize a certain performance metric. So the federation utility, so we first had the user equipment utilities, how to derive the federation utility. There is also a trade-off to be made. We can have fairness, where we, for instance, use the minimum of the UIs allocated to the federation. That becomes the utility of the federation, so the minimum UI utility, or we can maximize the overall utility, where we just do a sum or an average over these the UIs associated to that federation. We can formulate the federation resource allocation problem as follows. So at the right side, you see the symbols and their explanation. So F is a set of federations, K is a set of user equipments, and then we have 3 binary values, where the first one, X, denotes if the user equipment K is in a federation F, Y is if CSP S is allocated to the federation F, and the last binary value depicts if a federation is used or not. So we want to maximize the overall user utility function. Constraint 1 ensures that the utility of a federation is not negative. Constraints 2 and 3, they upper and lower bound this binary value ZF. And constraint 4 ensures that every user equipment is assigned to a federation and is not assigned to more than one. And then lastly, constraint 5 ensures that the CSP is not shared among these multiple federations. And then the last 3 constrain the domain of the binary values. The next problem, or another problem or challenge, is grouping these users. Given that we could not exhaustively query this article to find the best groups, we opted to apply an heuristic method. So first we generate a set of sample CSP constellations. This can be random or already tailored to some of the applications in RadioWeaves. And we compute the utility of each UI per set of CSP constellations. And then this utility function per CSP constellation is used to group utilities, the users which have a good utility to a certain CSP constellation, and a certain CSP constellation. And we applied, we checked what we have done in the framework, and here are some initial results to show how the RadioWeave or the federations are formed based on 2 different applications, for instance. So in the first application is wireless power transfer. There, for the utility, we applied a very simple or first exploration is that we assume that we have coherent operation mode, and then giving the certain CSPs that are chosen, that we have coherent constructive interference at the user equipment side. And we assume IID Rayleigh fading, so it is the sum of these received signal amplitudes, and then we divide this by the maximum achievable power at a certain location in the RadioWeaves to normalize it between 0 and 1. This is for wireless power transfer. And for the positioning, the utility is defined by maximizing the difference between the elevation and the azimuth angles between the CSPs. So by doing this, so at the top right, you can see the red color, which is the CSP, and the green is the served or target user equipment. What you want to do is maximize the difference between the thetas and the phi, so the azimuth and elevation, to ensure that we have a certain spatial coverage or that we maximize the spatial coverage of these CSPs. And the results show in blue for the wireless power transfer and the red for the positioning show that we have closely located users, CSPs at one side for the wireless power transfer, while for the positioning we have a more widespread usage of these CSPs to provide the positioning system or positioning. So ongoing and future work. So we will implement different algorithms for the CSP allocations to the federation. So we now have implemented the very basic stuff. And we want to improve the Oracle with more detailed utility functions. As I said, we first use the coherent operation mode and to maximize the spatial diversity for positioning. So we want to include other utility and more detailed utility functions as well. We want to include RadioWeave specific channel conditions. So now it was a ID Rayleigh. So we want to have a more accurate channel condition model. And lastly, we want to implement this in our tactile testbed. Thank you for listening.